right, welcome to my second talk. This talk is on building responsive and scalable .NET applications and components, and I'll be focusing specifically on performing I/O-bound asynchronous operations. I know some of you are here this morning, but we are recording these, and some of you may not have been here this morning, so I'll do a brief introduction to myself. I represent the company called Wintellect. We are a training and consulting company. I will be your host. My name is Jeff Richter. I'm one of the co-founders or owners of the company, but most people are familiar with me from the various books that I've written. My most recent book came out in December of this past year. And then again at the bottom, if you want to find me on Facebook or what are the other ones? Google+, Twitter, or LinkedIn, then I will be happy to be your friend. During lunch, I checked, and some people are already befriending me, so that's good. That's good right there. I haven't accepted yet, but I'll do it. Worst case will be this weekend, after I get back home to Seattle. At the bottom of the slide is a link to the Wintellect blog, where we have lots of blog posts about many technology-related things. And then at the very far bottom is my email address, where you're welcome to contact me there. Okay. I do want to mention that in June of this past year, Wintellect announced Wintellect Now, which is our online video training service, where we have a lot of videos for technical content. We just hit our 250th video this past week, and we're hoping to hit 500 by the end of the year, and I think we're very much on track to do that. So try it for free for 14 days. You can use the promotional code here of Jeffrey R 2013, or there's another one that was given out to all of you attendees at the conference. All right, so with that behind me, now I will start focusing on the technical content of the talk. So I've been working with threads since they were first introduced in the Windows operating system, I'm guessing around 1990 or so. So like 25 years, thereabouts. And during that time, these past 25 years, I've really learned a lot. And I've done a lot of work with them and gained a lot of experience. And it's come to my attention that the way a lot of people understand and think about threads is not really the best way. So let me start off by just doing some thread fundamentals here so that we're all on the same page as to what exactly is a thread. What exactly does it do for you, and what is the cost associated with a thread? Like almost every operating system feature, it's not free. There's some kind of cost that's associated with that feature. Well, if you go back and look at early operating systems, this is certainly true of Microsoft operating systems like MS-DOS or 16-bit Windows, but it's also true of operating systems made by other vendors as well. These early operating systems, there was no concept of a thread. There was no such thing. We didn't even have the term. No one ever discussed it at all. And there was a problem that existed with these early operating systems. And the problem was that if an application entered into a long-running task, like printing a document, or some big calculation, compiling of code, or, I mean, maybe you have a bug in your code and it goes into an infinite loop. That's certainly a long-running task. Then the entire operating system, the whole machine, everything would completely freeze. In fact, I was a 16-bit Windows user for a long, long time, and when I wrote programs that had a bug in it, which would go into an infinite loop, and yes, I did do that on occasion, then the whole machine would freeze, Alt-Tab would not work, in fact, Control-Alt-Delete wouldn't work either. And the only way that I could get control back on the machine is to literally power the machine down, power it back up, reboot, re-log in. Any applications that I had been running, they were killed when I powered down the machine, so I had to restart all those applications. Any data that I had entered into those applications, like Word, PowerPoint, Excel data, if I had not yet saved that data from memory onto disk, then that data was simply thrown away as well. And then I would have to re-enter that data in again. Now, needless to say, this was a horrible experience for end users. And Microsoft knew this. Microsoft also knew that within Microsoft, they didn't have any employee there who really had experience building secure, reliable, robust operating systems. So Bill Gates looked outside of Microsoft to try to find someone in the industry who did have that experience. And he found a guy who worked at Digital Equipment Corp on other operating systems like VMS, brought him to Microsoft. He brought a lot of the people he'd worked with over to Microsoft as well. And then they started architecting and building for Microsoft a new 32-bit operating system that was secure, reliable, and robust, and all the good catchwords of the day. One of the things that they did as they were designing this operating system was they introduced a concept of a thread. And a thread is a virtualization technique, just like a process. In Windows, a process virtualizes memory. And in Windows, a thread virtualizes the CPU itself. Now, like with all virtualization technologies, there's some overhead involved. That overhead usually comes in the form of both time and space. Space meaning memory consumption, and time meaning execution speed, how fast the operating system is going to run. So they came up with this idea of putting threads into the system, which, as I say, is a way of virtualizing the CPU. And then what happened was every process, every application would run in a process, so it would get its own address space or memory. And then within that process, a thread would be created, which would be a virtualization of the CPU, so the CPU could access that memory. So now when the user ran multiple applications on the machine, like Word, PowerPoint, and Excel, each one of those would get its own thread. And the operating system would take one of those application threads, put it on the CPU, and let that application run for a period of time, which we call the quantum. And the quantum is about 30 milliseconds or so. When the quantum would expire, the operating system would switch away from that one application and then switch to another application's thread, put it on the CPU, and let it run from a quantum. And then when the quantum was expired, again, switch away, switch to another one, and let that one run on the quantum. And the operating system just keeps doing this thread switching over and over and over again, about every 30 milliseconds or so. Now, the beautiful thing about this is that if one of those applications entered into an infinite loop, that means that whenever that thread was on the CPU, it would execute that infinite loop for about 30 milliseconds. And then when the 30 milliseconds expired, the operating would switch away to another application and allow it to run. So even though applications could go into infinite loops, they were really only running in that infinite loop for 30 milliseconds, and then the operating system would let other applications to make forward progress. And this meant that the entire machine no longer froze. That was really the big benefit, is that when one application entered into an infinite loop or long-running task, like printing a document, the machine itself was no longer completely frozen, and other applications were still able to make forward progress. In fact, the user could now use another application like Task Manager, and then use Task Manager to kill the application that was in an infinite loop. Now that application would die, and any data that was in memory that it did not save to disk, that would be destroyed. But the other applications, they would continue running just fine, and they were totally unaffected by this. The user would not have to reboot the machine. The user would not have to re-log in. The user would not have to restart all those applications, and the user would not have to re-enter in any data for those other applications. And that's really why threads were created. So 20-some years ago, threads were introduced to enable this ability. And basically what it boils down to is it allows the Windows operating system to be more reliable and robust and responsive to the end user. Really, threads allow one application to go into an infinite loop while allowing other applications to continue to make forward progress. Okay. Now, a lot of times people say, well, I want my program to run faster, so I'm going to use more threads. No. That's not how that works, okay? Threads have overhead associated with it. So every thread you create, you are allocating more memory and you are wasting more time. So the system doesn't actually run faster at all. In fact, the more threads you have, the slower the system actually goes. So you really want to have as few threads as possible. Now, the reason for this is because threads have overhead associated with them, and that's what I want to focus on. So whenever you create a thread, the operating system has to allocate a block of memory called the thread's kernel object. And the operating system uses this to manage the thread's existence over its lifetime. It has a lot of properties in it, like the date and time when the thread was created, the number of times the thread's been scheduled to a CPU, the priority of the thread, the state of the thread. All of that information is embedded in the kernel object. Now, the size of the kernel object varies. That is, how many bytes it is, varies depending on the CPU architecture that you're running on. Today, Windows supports 3 CPU architectures. They are the x86 architecture, the x64, and the ARM. In the past, Windows used to support other ones, but those have all been dropped. These are the only 3 that are still supported today. So this gives you an idea of approximately how many bytes the kernel object is for any given thread. In addition to the kernel mode data structure, every thread is allocated for it a user mode data structure, which we call the thread environment block, or TEB for short. And on all the CPU architectures today, the TEB is 4 kilobytes in size. The TEB contains the exception handling chain. That is, whenever your thread enters into a try block, there's a node that's added to a linked list of the try block. And whenever your thread leaves a try block, there's a node that's removed from the linked list. So if your thread throws an exception at some point, the operating system goes to that thread's thread environment block and then starts walking the nodes on the linked list, trying to find a catch block that wants to handle the exception that was thrown. If the operating system goes all the way through the linked list and doesn't find a handler, then we have what is called an unhandled exception. You saw one in my presentation earlier today when I got the catastrophic one. And then by default in Windows, whenever any thread in a process has an unhandled exception, Windows terminates the entire process. The most significant piece of overhead for a thread are its stacks. Every thread has both a user mode stack as well as a kernel mode stack. And the user mode stack is 1 megabyte of memory. So you need to say to yourself, whenever you create a thread, I am allocating a megabyte of memory. I'm allocating a megabyte of memory. And it's really worse than that, because it's only 1 meg for the user mode stack, but it's another 12K or 24K for the kernel mode stack. It's 12K on a 32-bit system, and it's 24K on a 64-bit system. Then you have the 4K for the user mode tab, and then you have another kilobyte or so for the kernel object up above. And in addition to all this memory overhead, which, by the way, when you create a thread, the system has to find all that memory to allocate it, so that takes time. And the system has to initialize all that memory. That also takes time. And when a thread dies, the system has to free all this memory back up. That also takes time. So in addition to all the memory overhead, there's all the time overhead as well. Windows has this other policy, which when they were originally designing the system 20-some years ago, this policy made a lot of sense. But today in Windows, they really regret this policy. When they were first designing Windows NT many years ago, they endowed the operating system with this feature called thread attach and detach notifications. Whenever a thread is created in a process, Windows notifies all the DLLs in the process that a new thread is being created. And whenever a thread dies in the process, Windows notifies all the DLLs that the thread is dying in the process. We call that a detach notification. Well, in the early days of Windows, it was common for processes to have 5 or maybe 6 DLLs. So only 5 or 6 DLLs needed to be notified of these attach and detach notifications. But today in Windows, today it is very common for processes to have 250, maybe even 300 DLLs loaded in the address space. So now whenever you create a thread, 250 or maybe 300 DLLs will receive the notification that the thread's being created. This is an enormous performance hit. And when the thread dies, again, another several hundred DLLs are notified, which is again a performance hit. So creating threads is very expensive in terms of memory and also in terms of time. The next thing you have to realize is that a single CPU can only do one thing at a time. So what Windows does is it puts a thread on the CPU, again runs it for the quantum, then takes it off, puts another thread on the CPU, and runs it for a quantum. And so if you only have one CPU and you have thousands of threads, they each get to run one after another, but only for 30 milliseconds at a time. They can't all run at the same time. Okay. And what Windows is doing is performing this thing called a context switch that happens every 30 milliseconds. And where Windows has to save the registers in the CPU off to the currently running thread's kernel object, then pick another thread, grab the CPU registers out of its kernel object, put it on the CPU, let it run for 30 milliseconds, and then just keep doing this over and over again. The point that I'm trying to make here is that these context switches are also not free. That's a wasted time as well, because the system has to do this. And it's happening every 30 milliseconds, so it's happening quite regularly. So all of this is pure overhead. And all of this really hurts performance quite significantly. So then you might ask yourself, so then why did Microsoft do it? If there's so much, why did they add threads to the operating system if there's so much wasted memory and so much wasted time? Well, and the answer is because they wanted to provide users with a robust, reliable operating system, where an application could go into an infinite loop and other applications could still make forward progress. That's why this was done. So the conclusion that you should draw as a software developer from this is that you have to avoid threads as much as possible. I love threads, and I also hate them at the same time. And when you are architecting your software, you want to avoid the use of threads as much as possible because they consume so much memory and they waste so much time. Of course, there is a corollary to that. And the corollary is you do want to use threads because that's what made the system responsive. So in your own application, if in order to keep your user interface responsive and responding to the user's mouse events and keyboard events and touch events, you want to take any computationally intensive work and you want to put it off onto another thread so the user interface thread isn't busy doing that and can respond to user input. And if you are running on a machine that has multiple CPUs, which today, finding multiple CPU machines are very commonplace. But for the record, when Windows NT was being created 20-some years ago, computers that had multiple CPUs in them was very rare, practically non-existent. Today, multiple CPU computers is the mainstream. In fact, it's even hard to find a computer with only one CPU in it today. So if you are running on a computer with multiple CPUs, and today most likely you are, then Windows does have the ability to put one thread on one CPU, another thread on the other CPU, and then they can run simultaneously. And this allows you to get a performance improvement because now, and only now, you're able to use threads. You can have 2 units of work done in 1 unit of time by putting threads on the different CPUs. But that's the only time threads give us a performance improvement is if we're on a multi-CPU computer, a computer with multiple cores. Okay, so now I have a demo for you that will let you see the overhead that's associated with the threads. Here in Visual Studio, I have a piece of code. First thing I do is I declare an integer, 1 megabyte, and I set it to 1024 times 1024, which is a megabyte. And then I'm going to use that variable a little bit further down. Then I'm going to create a manual reset event, which I'm not going to talk about in great detail, but effectively this is a Boolean variable. A manual reset event is a Boolean variable, and I'm initializing the Boolean to have a value of false right over here. Then inside the using statement, I am creating an integer, which is, I'm just going to use it as a counter. I initialize it to 0 to indicate how many threads I have created so far. Then I enter a try block, and then I enter an infinite loop while true. And inside the infinite loop, I am newing up a brand new thread. Then I'm going to start it, which actually causes the thread to be created in the system. And now that I've created this new thread successfully, I'm going to add 1 to the thread num to indicate that I've created 1 thread. And then over here, I'm going to say, hey, Windows, for my process, how much memory is it using right now? Now, Windows returns that to me in bytes. and I'm going to show it to you in megabytes, so I divide it by 1 megabyte. And here you can see in the console window, which I'll move off to the side, that after creating one thread, my process is now using 120 megabytes of memory. Now, we can't tell how much of that memory is for this one thread that I just created. So let's loop around, and let me do something else really quick first. I want to pin this to the top. Okay, so now I'm going to loop around, and I'm going to create a second thread. And now we see that after creating a second thread, I'm up to 134 megabytes of memory. Now, this is unusually high. This makes it look like creating a thread just allocated another 14 megabytes of memory. That is not true. There's some other stuff that must have happened here. But let's loop around some more. Now we're at 135, so this makes more sense, because it does make sense that each thread allocates about a megabyte of memory. Here, but it is a little bit more than 1 megabyte, so here it looks like 2. That's because of some rounding error. And now what I'm going to do is I'm just going to hit F5 and let this run. So my program is now creating threads as fast as it possibly can. And you'll notice that the amount of memory is just skyrocketing. It is forever increasing number. And approximately, with each thread that I'm allocating, each thread I'm creating, I'm allocating 1 more megabyte of memory. Now, there's a question that people ask me very frequently. And that question is, hey, Jeff, in my program, how many threads will Windows allow me to create? My answer to that, I have a standard answer for that, and it's always the same thing. It is, your architecture is broken. That is my answer. If you're asking me, or anybody, how many threads can I create before the operating system stops you, you're going down a very bad path. You're really asking yourself, how much resources can I just waste until the operating system purposely stops me and won't let me do any more? That's not the right way to write software. The right way to architect software is to try to figure out how few resources you need in order to get the work done that you need to get done. Now, that being said, this program will stop. And when it stops, you will see the number of how many threads you can create in a program before Windows stops you. And we're getting close. You may also notice that this has gotten slower, right? It's getting slower because the system's allocating more memory. It doesn't have the memory, so it's doing swapping to the paging file on the hard disk now. And more swapping is occurring, and then that's a performance hit, of course. Okay, we're really close. I've done this before, so I know. There it is. Okay, so if anybody asks you, how many threads can I create in a program? The answer is 1,505. Okay? So now you know, you have an answer for that question. And the reason why it's 1,505 is because after that, we've run out of memory. In fact, you'll see here in my code, I caught the out-of-memory exception. So what really limits the number of threads that you can create in a process is not that the operating system has some hard-coded limit. It's that eventually you run out of memory, and that's what prevents it from happening. So the purpose of this is to show you that memories have some pretty significant threads have some pretty significant memory overhead associated with them, and the more of them you create, the less memory you're going to have for other things. In fact, right now in this program, all of the program's memory is occupied by thread stacks. If I want to load, let's say, a document into memory, an email message, a word processing document, a spreadsheet, there's no more memory left over in this process for me to load that in. All the memory is currently being consumed by threads. So that's no good. Okay. So this demonstrates for you the overhead that's associated with threads, and hopefully you see it. So before I go on to the next slide, I'll just do one more thing with you here. So I've just told you what the maximum number of threads is that you can have in a program. But what is the ideal number of threads to have in a program? So what should you really be striving for? You know you shouldn't be getting 1,500. That's way too many. But what should you be striving for? Well, if we had a computer with only one CPU in it, and what we cared about most in the world was raw performance and efficiency. We want to write our code so it is the most efficient code possible and ran as fast as possible, then what would be the right number of threads to have on this single processor machine? 1. Right? If we had 2 threads on a single processor machine, then we would have context switching introduced, which would make things go slower. So we'd actually be allocating a new thread and then hurting performance. So we're wasting memory and we're wasting time. In this case, the less stuff we do, the faster it's going to run. Okay, so let's say we're now on a computer that has 2 CPUs on the motherboard. So in this case, what would be the ideal number of threads to have? Right? 2. Right? So if you're having trouble following the formula is n equals n, okay? Where n is the number of cores and n is the number of CPUs. So in an ideal world, when you are designing an application, the number of threads that you should have in that application is no more than 1 per core. Okay, that is the ideal situation. And you want to strive for that. Now, I'm not going to say you're going to get that goal. I mean, you're going to necessarily make that happen, but that is the goal that you should be striving for. It's certainly what I always strive for whenever I'm designing software. So, what can you do to help you to attain that goal? Well, that's what we're going to be talking about now. So, what I show on this slide here is a depiction of a typical computer system. Your typical computer system has probably some kind of network controller that's connected to it. And you might have a DVD-ROM drive on your computer too. And you might have a hard disk that's on your computer as well. Now, if you look closely at all of these devices, you see they all have circuitry. You can see the circuitry clearly for the network over here. What is that circuitry about? Well, that circuitry knows how to read bytes in from the motherboard, convert them to electrical signals, which are then sent to a wire, which you would plug into the back. And of course, it knows how to do the reverse as well. The DVD-ROM drive, if you take the cover off of it, you would see that there's circuitry there. That circuitry knows how to spin the platter, shine the laser light at it, interpret the reflection, and then send the bytes that it's reading off of the platter through a wire that you would plug into the back and the other end on the motherboard, and that's how you read the bytes in from the DVD-ROM drive. If you look at the hard disk over here, if we were to flip it upside down, we would see that there's circuitry on it too. And that circuitry knows how to spin the platter, seek the head to the right location, do its magnetism thing in order to read or possibly write bytes to the disk that would be sent or received over a wire that you would plug into the back. The point I'm trying to make here is that all these hardware devices, they come with their own computer. The circuitry is computer. And so what does this mean for the CPU that's on the motherboard when you are attempting to do I/O operations? Well, that's what we're going to look at now. So let's just say that there's a file on the hard disk, and you want to write some code to open up that file and read some of the data from the hard disk into memory. How would you do that? Well, normally in .NET, the way we would do that is we would begin by writing code that news up a file stream. The file stream class in .NET will open up a file on the hard disk. And then we get back this variable fs, which is a reference to the file stream object. Now that we've opened the file on the disk, the next thing we want to do is we want to read some data in. So we're going to say file stream.read, and then we pass in some arguments. That's not important for our conversation. Now, what the read method does internally is it causes your thread to jump from managed code to native code, where it calls the Win32 function read file. This is a very well documented function. It's been around for several decades now. In fact, I think it is probably the most called Win32 function of all Win32 functions that exist. Now, what the read file function does internally is it allocates a small data structure called an IO request packet, or ERP for short. An I/O request packet data structure is about 100 bytes in size. It includes things in it like the handle to the file that you wish to read from, the offset within the file where the read should begin, the number of bytes within the file that you wish to read, the address of a byte array where those bytes should be placed. All of that information is embedded inside the I/O request packet. Then the operating system takes your thread and has it jump from user mode to kernel mode, and it passes the ERP data structure into the operating system itself. Now the operating system looks at the contents of the ERP and sees that this is a read request against the file on the hard disk. Every hardware device has a device driver in the operating system that manages that hardware device. And every device driver has what's called an ERP queue. I only show here on the slide the ERP queue for the hard disk, but every hardware device would have its own ERP queue. I just didn't put it on the slide for all of them. So now what Windows will do is it will take the ERP packet that I've passed down and it will dispatch it over to the ERP queue for the hard disk, since this is an attempt to read data from the hard drive. Now what's going to happen is the device driver is going to take that ERP off of the queue and it's going to send it off to the hard disk over here. So now the hard disk spins up, it starts seeking the head, it starts doing its magnetism stuff, and so on, as it's trying to find those bytes on the hard disk so it can read them off and put them into memory. But here's the interesting part. While the hard disk is doing that, what is your thread doing that executed all of this code? And the answer is nothing. The CPU on the motherboard has nothing to do while an I/O operation is occurring in hardware. So because the CPU on the motherboard is the thing that executes threads, and it has nothing to do while performing an I/O operation, the CPU, your thread ends up being blocked and does not get to make forward progress at all. Now, you might think this is fine, but it's not. Okay? Remember, threads have overhead, right? You paid a big expense in order to create this thread. You wasted time to create the thread, and you allocated a megabyte of memory. And now the thread is sitting here doing nothing, which means you've wasted all of that energy that you've created, and that makes your program very inefficient. Now, to make matters worse, the thread pool, which I'm hoping you use, because the thread pool is an awesome technology, and you should all be using the thread pool to manage your threads. But the thread pool, which tries to manage thread creation and destruction for you in an efficient way, that's its purpose in life, it has a feature. Although the way I describe it right now, it's not going to sound like a feature, it's going to sound like a bug. Okay? But it is a feature. If the thread pool thread is the thread that's executing this code, when Windows blocks a thread pool thread, Windows notifies the thread pool and says, thread pool, one of your threads, it's not running on a CPU anymore. And then the thread pool says, but wait a minute, I have a bunch of items that are queued up, and this thread is not running on the CPU. That's no good. That means these items are just sitting here. So what the thread pool does is it goes and creates another thread. This is very inefficient because it's now allocating more memory and wasting more time, and it's doing it because you have a thread already that's not running. It goes and creates another thread, which is, this is its best way it can, is the best thing it can think of, really, for how to continue to get more work done. But it's not an ideal situation. So the point that I'm trying to make here is that when a thread pool thread stops running for any reason, and in this example, it's happening because of an I/O operation, the thread pool compensates by creating another thread. This is a very expensive way to compensate for this problem. It's the best thing it can do, but it's really very inefficient and not ideal. And this is how we can end up getting more threads in our program, Remember, we just said a moment ago, on a computer with one CPU, we really should only have one thread. On a computer with two CPUs, we really should only have two threads, and so on. Well, in this case, if this is a single CPU machine, I have one thread, but because it blocks, the thread pool creates another thread, so now I have more threads than I have CPUs, which is now just wasteful. It's just wasteful. Okay. Now, eventually, the I/O request will complete, and when it does, the thread will return all the way up the stack. So then it does get scheduled back to a CPU, and the thread does get to return all the way back. Then you get the number of bytes read, and voila, the I/O operation is done. So what I'm showing you here is the way that most people perform I/O operations, but it is incredibly inefficient. And if you are trying to write software that scales well, that can handle 1,000 client requests a second, 10,000 client requests a second, 100,000 client requests a second, this way of architecting the code is very bad, and you will not achieve those kinds of numbers no matter what. Furthermore, if you're trying to build a graphical app, if you execute this on the GUI thread, then the GUI thread will block over here while the I/O operation is occurring, and therefore any input that the user is generating, mouse events, keyboard events, and so on, the thread is stuck waiting for the hard disk to return those bytes, and so the input that the user is generating is not being processed at all. And then the user has a bad experience working with your application because it is being non-responsive. So we want to fix this. So we want to build software that is scalable. We want to build software that is responsive to the user. That requires that we make some changes to the way we architect our software. So that's what I will show here. So I'm going to take the same code we had before. I want to do the same thing, but I want to do it in a more efficient fashion. So the way we accomplish it is I new up my file stream. But when I new up the file stream, I now pass in a special flag called file options asynchronous. This special flag says two things to the device driver. It tells the device driver, don't block the thread requesting an I/O operation. So now the thread won't block, which means the thread pool won't create another thread. So that's how we're going to get our efficiency back, by doing that. The second thing the flag does is it tells the device driver to put the completed ERP into the CLR's thread pool. I'll talk more about that when I get to it a little bit later on. Well, after I've newed up the file stream, I'm now going to call read async instead of read. Read async is a new method that was introduced in .NET 4.5. And there's actually a lot of async methods that were introduced in .NET 4.5. What these async methods do is all pretty much the same thing. When you call an async method, internally, they create an I/O request packet, they send it down to the device driver, and then they return a task. And that's what will happen here. So when I call read async, it will internally call read file. Read file will create the I/O request packet exactly like it did on the previous slide, and then the I/O request packet will be sent down to the operating system. The operating system will then take the I/O request packet and will shove it into the ERP queue for the desired hardware device, in this case the hard disk. But now a beautiful thing happens. Because we use that flag, file options asynchronous above, your thread will not block here now. And instead, your thread is allowed to return all the way back up the call stack here, where read async will return a task object. And then in .NET 4.5, a new thing we can do with task objects is we can await them. And this await allows the thread, your thread, to go back to wherever it came from. This is awesome, okay, just awesome. If it's the GUI thread, that means that the thread goes back to the message pump where it can continue to process user input, like keystroke messages, mouse messages, and so on. So now your user interface is responsive to the user. Well, you have to love that. If this was a thread pool thread that does this, then the thread pool thread will return back to the thread pool where it can go and process other things, so the thread pool doesn't have to create another thread. So that's going to keep your resource consumption very low, your performance very high. So you have to love that too. Now, the next thing that happens is the device driver will take the I/O request packet and will send it off to the hard disk. So the hard disk spins up, it seeks the head to the right location, it does its magnetism thing, and then it eventually reads the bytes that you desire into memory. After that is complete, the device driver is going to take the I/O request packet and it's going to queue it up to the CLR's thread pool. This red box here represents the thread pool that comes with the common language runtime. Well, whenever any item gets queued up to the thread pool, what happens next is a thread pool thread extracts that item from the pool and then goes and calls a callback method. And what will happen here is a thread pool thread will take the completed ERP out of the pool and will go and call back this method up above. But what's interesting is that instead of calling this method and have it execute from the beginning, which is usually what happens when you call a method, this method is implemented as a state machine, and the thread pool thread resumes the state machine. And what that really means is when the thread pool thread calls this method, it will continue with the assignment. It won't new up the file stream, that was already done. So it'll go to the next state of the state machine, which is come back to the assignment here, get the number of bytes read, and continue running. So the whole purpose of this async and await feature that was added in C# 5.0, here's the elevator pitch for it. Okay? Await and async and await in C# 5 allow you to have a sequential programming model for writing code that performs I/O operations without blocking any threads, thereby allowing you to create more responsive and scalable software. Okay? That is the summary definition of what async and await was all about. Allows you to have a sequential programming model where you new up the file stream, then you read some data, then you process the data. So you're writing your code sequentially, the way that you're used to, the way that you're familiar with writing the code. But we don't want to block any threads that are doing I/O operations because that's very inefficient. So this allows you to do it without blocking any threads. That allows you to build more scalable and responsive software. Okay, so now, I have a demo here in Visual Studio to show you a little bit about what's happening underneath the covers when we use async and await in our code. So I've just started this program in Visual Studio, and so the primary thread is calling into this method here. Now, every thread is assigned an integer ID value, and they're always unique. And on this first line of code here, I'm going to get the ID of the thread that's executing this method. And here, if we look at it in the debugger, you can see that it has an ID of 10. Hopefully you can see that way in the back. But it says 10. Okay? So the primary thread of this program has been assigned an ID of 10. Just remember that. I'm going to come back to it a little bit later. Now, the next thing I'm doing is I'm calling this method HTTP_length_async, which I have right below. So I'm going to hit F11, and I'm going to step into it. And then if I were to ask you, what thread is calling this method now? Is it the same thread, or it is a different thread? Well, hopefully you would say it's the same thread. And to prove that it is, I will go and get the ID of it. And if we look at the ID, we're hoping to see the number 10. And we do. Okay, so this proves it's the same thread that called from one method to the other. Excellent. Now the next thing I'm going to do, inside here I want to make a web request. So I'm newing up an HTTP client, and then I'm going to call this method getStringAsync. Well, here you see there's an async method. Now remember, almost all async methods do the exact same thing. Almost all of them create an I/O request packet, send it down to a device driver, and then return a task. And that's what's going to happen here. This case, it's a network request, so it's going to the network device driver instead of a hard disk request, which would go to the hard drive device driver. So this is going to create an IO request packet, send it down to the driver, and return back a task. Now, the device driver will actually do this IO operation in the future. Now, I take the task that came back, and here you can see this returns a task of string, and then I'm going to await it. The await operator in C# says, I do not want to wait for the IO operation to complete. I want to allow the thread to go back to where it came from. Now, what I'm going to do is I'm going to hit F10 to single step to the next line of code in the debugger. And watch what happens when I single step to the next line of code. Here I go. You'll notice we go up. We don't go down. That's because the await operator allows our thread to return. Again, if this was the GUI thread executing this, the GUI thread would go back to the message pump, so the user interface would stay responsive. If this is a thread pool thread that was executing this, then the thread pool thread would return back to the pool, so it can go and do other things. But we're not blocking the thread. And that's what's preventing us from wasting memory and time creating other threads. That's the feature here. Now, up above, I'm going to hit F10, and then I'm going to say, so what is the ID of the thread that we're on here? And I'm sure it's not surprising to you, but this comes back with 10. So this is indicating that it is the primary thread, and it has returned from that method. Now, the next thing I do over here is I'm taking the task that I got returned from calling this method, and I'm going to block until this IO completes. This is a terrible thing to do, what I'm about to do. Okay? You should not do what I am doing here. I am a trained professional, however. Do not try it at home. Okay? But I'm doing this for demonstration purposes. I would not ship code that had this in it. And by taking the task and calling getAwaiter getResult on it, this will block the primary thread until the task has completed. That is, until the IO operation is done. And blocking threads is bad, which is why you do not normally want to do that, but this is doing it here. But I'm just doing it because I want to demonstrate this for you, not because I would do it in real life. So I'm going to hit F10 on this call to get results, and you'll notice that where we end up next is nowhere. Okay. So unfortunately, I spoke so long that the IO operation timed out. So that's a bit of a bummer, but let's see if I can do it again. Let's rewind this up to here. Now I'm going to hit F11. I'm going to come in here. I'm going to do this again. Now I'm going to come back out. And now I'm going to hit this. And then we go over here. See, I didn't waste as much time. So the IO operation didn't time out now. So I have the primary thread stuck in the call to get result, but somehow I ended up over here. This can't be the primary thread. If the primary thread is in get result, then it has to be a different thread that is at this debugger break line down below. And in fact, it is. If I come over here and I get the ID of this thread, we see it has an ID of 20, not 10. Therefore, it must be a different thread. And in fact, this is a thread pool thread that has come into here. So what's interesting about this is that the primary thread executed this code, but then a thread pool thread executed this code from here down. Two different threads were inside this one method at different times. Now, this code down here is going to get the string. So here's the string that came back from hitting Microsoft.com, the HTML that was returned from the server. And then over here, I go and get the length of that. That's 1,020 characters in that string. And then I go and I set this text over here, which is now going to cause, now this thread pool thread is going to return back to the pool, but the primary thread is waiting for that result. And so when I hit F10, we end up back over here. And now the primary thread is waking up because what it was waiting for has now completed, and it's getting that length, which we can see here is 1,020. Okay? So if I did not have the call to get result here, then no threads would have been blocked in this program. And therefore, the threads that we did have, we could keep reusing them over and over again, and that allows the software to be more efficient. Now, how would you get rid of this over here? Normally, the way you would get rid of this call to get result, which is a blocking call, and we don't like the blocking calls, is we would have awaited this. So we would have said await task here. That would have allowed the thread to go back, and then when the length came in, another thread could have come in, gotten the length, and then continued the execution. So the await thing just percolates itself up all the way through your call stack. You just put it everywhere all the way up, and that allows all the threads to keep returning back so that your program stays efficient. So now I'm just going to put a little bit of icing on the cake in about the 10 minutes we have remaining. This just shows an example where I'm doing a client piece of code that's going to make a request to a server, and then the server is going to send a response, and then the client's going to wait for the response, and then it's going to process the response. In this particular example, I happen to be using a name pipe client, but that's not really important in this example. I do set some properties on it, but again, that's not important in this example. But what is important is I'm taking the message that gets passed in, I am UTF-8 encoding it into a byte array, and this is the data that I want to send from the client to the server. So I take my name pipe, I call write async on it, and I pass in my byte array. Now, write async, like all the other async methods, it creates an IO request packet, sends it down to the device driver, returns a task. Then I await that task, which allows the thread to return back to the caller, so it can go do something else. Then, when the request is sent to the server, a thread pool thread will come in next, new up a byte array, and then call read async. Read async will create an IO request packet, send it down to the driver, return a task, which again, I await that task. That allows the thread to return back from where it came from. So then in the future, when the server sends the response back and the client has read it, then a thread pool thread would come in after the await, get the bytes read, I do a UTF-8 decode on that, now I have a string, and when you write the code like this, I'm doing request response, which is a very popular programming pattern that programmers like, but because I'm calling async methods and I'm awaiting the result of them, no threads are blocked in this program, which means the user interface stays alive and well, and it also means the thread pool can use threads very efficiently. Okay, this slide here just says that there's a bunch of async methods in the framework class library, and you should look at those and try to use them. But now I have these two slides. I only have about 8 minutes to go, and it's going to be a little bit of a push, so I'm going to go fast here. But these two last slides are really important slides. So on this slide here, I want to show you how to build a non-scalable server. Now, typically, this is not a goal, right? Normally, you don't wake up in the morning and say, hey, I want to write the worst software possible. So let's see what I can do to really mess the world up and make it a worse place to live in. However, while this is not a goal, it is what most people do. It's the default. So now I want you to see why when people do the default thing of what documentation tells you to do and samples tells you to do and what a lot of guidance tells you to do, I want you to see why it's really very bad guidance. In this scenario here, we have 3 players. I have clients over here. I'm choosing Internet Explorer for the clients, but you could replace these with any clients. It doesn't matter. These clients are going to make a request of a server. That's the big green rectangle. Now that server could be any kind of server. I'm saying ASP or maybe WCF, but it doesn't matter, any kind of server. And when those client requests come into this server is going to make a request of another server. I'm saying SQL server, but it could be any kind of server. It doesn't matter. The architecture is always the same. So let's walk through what's going to happen. The first client makes a request into the server. Well, those requests, they come into the thread pool. So the thread pool is going to create a thread to process this client request. So now the thread pool thread comes out and it starts executing your code to handle the client request. Now, a very common thing is that your code wants to make a request to another server, like SQL Server. And if you do that synchronously, which is what we have all been taught and trained to do over our computer science careers, then that thread pool thread is going to block there when it makes the request. Because that thread is blocked, when another client request comes into the server, the thread pool has to create another thread because it can't use the first one because it's blocked. So the thread pool does create another thread. Now remember, each thread is another megabyte of memory. So the second thread gets created, it makes a request to the server, and then it blocks. So then when the third request comes in, the thread pool has to create yet another thread that executes some code, it makes a request to the server, and then it blocks. So you see what's happening? This server is really spending all of its time creating threads so that they can stop running. Okay, very inefficient. Real waste of memory to do all of that. Now, to make matters worse, let's say that SQL Server is processing those three requests, and then it sends the responses back. Well, that's going to cause those three threads to wake up and continue executing. But if we're running on a computer with only 1 or 2 CPUs on it, and we have 3 threads that want to run, then Windows has to context switch between them and give each one 30 millisecond time slices as it loops around. And the context switching adds overhead, and that hurts performance. Then, after they're all done, those threads will all return the result back to the clients and go back to the pool where they can go and kill themselves. Okay? So if you were to write the biography of this server, it would be something like this. Threads are created so they can stop running, then they wake up so they can run slowly, then they kill themselves. Okay? And it's very inefficient, but this is the default. Now, in this model, by the way, a very common model, we are in effect using 1 thread per client request. Correct? Yes? Okay. So, how many client requests can this server handle concurrently at the same time? 1,504. Yes? Right? Because I showed you that earlier, right? The maximum number of threads you can create in a process is 1,504. And then we run out of memory and the server dies. So this can scale to handle up to 1,504 concurrent clients. And again, that's assuming that we're not actually doing anything with data. But if, let's say, we're making a request to SQL Server that's going to return some actual data back that we need to process, that's going to use up more of the memory, which means I can create even fewer threads, which means I'm not going to scale maybe even above 1,000 possible concurrent client requests, right? So the architecture is just bad. It's very inefficient. It's very bad. So now, let's fix it. Here is how to architect a scalable server. Now we have the same players. So I got the same 3 Internet Explorers, I got my green server, and I got my other server down below. So a client makes a request to the server this time. The thread pool does create a thread, and it starts executing code on behalf of the client. Now here's the real trick. This thread is going to make a request to SQL Server, but instead of doing it synchronously, where the thread gets blocked, we're going to do it asynchronously by calling an async method, and we're going to await the task that returns. So we make the request to the server, but because we're doing it asynchronously, the thread can go back to the pool. It can go back to where it came from. It's not blocked there, waiting for SQL to give a response. So now, when the second client request comes in, the same thread pool thread wakes up and does the same thing. Then it goes back to the pool, so when the third client request comes in, the same thread pool thread can go and do the same thing. Do you see what's happening now? We only need 1 thread in the server doing everything. Now, remember when I/O operations are executed asynchronously, the device driver is told to take the completed I/O request packet and to queue it up to the thread pool. So when SQL Server replies with these 3 responses, they will be queued up to the thread pool 1, 2, and 3. And then the thread pool will use the same thread to pull out process it, return the first result back to the client. Then pull the second one out, process it, return it to the second client, pull the third one out, process it, send it back to the third client. And again, we're using only one thread on the server to accomplish everything. Now, this code could scale easily to 1,000, 10,000, 100,000 clients, all being processed concurrently by this server. And writing the code to do that is really just simply a matter of taking any of your methods that perform I/O operations, modifying them to call the async versions, like read async and write async, instead of read and write, and then awaiting the result. So with a small modification to your existing source code, you're able to make your program now scale, and this is why that will happen. This slide here, which is my last one, and only 4 seconds to go, timing couldn't be better, is just to say to you that .NET has supports or fully supports the ability for you to create lots of different asynchronous servers. And I don't have time to go through all the details, but if you are building an ASP.NET web form page and you would like to make it asynchronous so that you scale better, go to the documentation and look up the async equal true page directive, and then you're going to have to call this method register async task, which is documented, so go and look it up. If you're using MVC instead, then you can derive your class from async controller and have your methods return a task of async result instead of async result. Then you can use awaits inside that method. If you're building an ASP.NET HB handler, then go into documentation and look up HB task async handler, which has a virtual method on it called process request async, and then you implement that, and then you put awaits inside there. And if you're doing a WCF service, then implement the service as an async function returning a task or task of T result, whatever you want to return, and then inside the method, call the async methods and put await in front of those. And if you just take that existing code, make these couple of changes to it, then all of a sudden your code should scale phenomenally well. And if it's a GUI app, then it should be much more responsive. Thank you very much.